In this video, we'll be approximating areas under curves. Our objectives will be to answer conceptual questions involving areas under curves. We'll illustrate, calculate, and compare right, left, and midpoint Riemann sums for functions. We'll evaluate Riemann sums from tables. We'll express given sums in sigma notation or evaluate expressions given in sigma notation. Let's go ahead and evaluate Riemann sums for large numbers of subintervals, whereas the number of subintervals increases as well. So this is going to be here, what we're talking about here is going to be the definition of a definite integral. It's really what that objective is talking about. So let's consider the function y equals f of x going from 0 to 6. Gives us this endpoint down here is 0, 0. This endpoint up here is 6, 6. And let's start asking what the area of this shaded region is that is under this line. Well, we notice that this is a right triangle, and we have a geometry formula for it, that it's 1/2 base times height. Our base is 6, and our height is also 6. So our area is going to be 18 square units. Now, we could have other ways that we can look at this. For instance, we could create some rectangles with right endpoints, because we know how to find areas of rectangles. Actually, before we do that, let's go ahead and talk about, that was kind of an easy example, but what if our function was curved like this, and we wanted to maybe from 0 to 6, we wanted to find this area that was in here. How would we do that? And we'd have to use some geometric figure that we know an area formula for, and right triangles are not going to do it for us. So we're probably going to either use rectangles and make the left side of the rectangle touch the function. See that? I can do that, and there will be some places where I'll have not enough area. There will be some places over here where there will be too much area, but hopefully they'll kind of balance each other out. Or if I don't want to do that, let's get rid of red here. I could maybe instead try to make right endpoints touch the function. And I'd have to have some number of rectangles that I knew that I wanted to make in order to do this, and some width. But I'd want all these rectangles probably to have the same width to make my life easier. But I'd do something like this. And in one instance, I'd get an answer that's too big, and in another instance, I'd get an answer that's too small. If I wanted to try and squeeze out some of that air, then I'd go ahead and I'd use the midpoint between those two values, between the left endpoint and the right endpoint, and I'd use that to help me figure out the area, and that's going to give me a lot closer estimate. So let's go ahead and let's look at this. If I used the right endpoints, let's draw this function again. Y equals x from 0 to 6. I want 2 rectangles, so I'm looking at a width of 6 that I want to cut into 2. So my delta x that I'm looking at is going to be 3. If I want the right endpoints, then I'm going to make this right endpoint here touch, and there's one rectangle, and then this right endpoint is going to touch, and then there's that rectangle. And I have my delta x of 3, and then I have this is going to be 3 plus 6. It's going to be 3 times 9 is 27. And we know that that's too big. 27 is too big because the actual answer is 18. So we say A is about 27 square units. This is an overestimate. Using our left endpoints this time. So we can try again. I'm sorry, using the right endpoints. So let's try using my left endpoints this time. And again, we have 0, we have 3, we have 6. And when we use the left endpoint, excuse me, then this is at 0. 3 times 0. Then left endpoint, that one's at 3. This one doesn't go anywhere. So this is 3. 3 times 3 is 9 square units. And this is an underestimate. Because again, we know that the actual answer is supposed to be 18. So let's try again one more time using the midpoints. So if I know that I have 0 and then 3 and then 6, the midpoint here is 1.5 and the midpoint here is 4.5. So let's draw that. We have 3. We have 1.5 is going to represent that. We have 6 and we have 4.5 is going to be representative of that. So we're going to make our height here for the first rectangle from 0 to 3. We're going to make our height here for our second rectangle from 3 to 6. We'll use the midpoint to get this piece will be a little bit too much, and this piece will be a little bit too not enough, and hopefully they kind of cancel each other out. And same thing there. So let's have 3 for our width, and then we have 1.5 for our height there, and then 4.5 for our height there. 5, 6.0 is exactly 18. This is exactly right. Now it's not always going to be exactly right. It's going to be an estimate, but we're going to see that the midpoint is going to be the best of the estimates that we're going to get, left and right. We're going to get the right answer will be somewhere in between. It'll be closer to the midpoint answer, and that midpoint answer is not always halfway in between the left midpoint and right midpoint. Let's look at our definition of a Riemann sum. Suppose that we have n, let's see, is this n? Yeah, n subintervals, I think. 1, 2, yeah, n subintervals from x sub 0 to x sub 1, x sub 1 to x sub 2. Maybe it's n plus 1 subintervals. Yeah, and then, but these are all cut up intervals of the interval from A to B. Each of these intervals has a width of delta x sub k for the kth subinterval that goes from x sub k minus 1 to x sub k. Your first subinterval is going to start at x sub 0, is what they're saying, and go to x sub 1 and so on. So you're going to use ordinal numbers here, starting at 1 Let xk with an asterisk be any point that represents that interval of x sub k minus 1 to x sub k for all k starting at 1 and going to n, so that it looks like this. And if I cut it, if I want 1, 2, 3, 4, let's say I want 4 rectangles, I'm going to have to cut it 3 times to make 4 intervals. So if f is defined on the closed interval a to b, the sum of k equals 1 to n of f of x sub k asterisk times delta x sub k is equal to f of x asterisk times delta x. This is x sub 1 asterisk, and this should be delta x sub 1. And this is f of x2 asterisk times delta x sub 2, and so on, that those delta x's should match what is in the index for that interval. Because delta x doesn't have to be constant. It is going to be constant the way that we do it. We're going to make our lives easier and make delta x a constant. That is called the general Riemann sum for f on the interval from a to b, and we'll be using that later to help define the definite interval. But for right now, let's approximate the area under the curve, and this is why I have my calculator over here. F of x is equal to 9 minus x squared from 1 to 3 using 4 subintervals. So my delta x is going to be 3 minus 1 over 4. Delta x, we're going to use the formula b minus a over n to calculate it. 2 over 4 is 1/2, or 0.5. So I need x, and then I need f of x starting at 1, then 1.5, 2.0, 2.5, 3.0. You'll notice that there's 5 numbers here. I'm going to use the first 4 for my left endpoints and the second 4 for my right endpoints. Let me go ahead and type in here 9 minus x squared. And I want my table settings for my independent variable to be on ask, my table to be there, and then I want to go ahead and figure out at 1.0, 1.5, 2.0, 2.5, 3.0. I'm going to use these later. So this is 8, and then 6.75, and then 5, then 2.75, and then 0. Now I also want to find the midpoints here, so I'm going to do m and f of m, where m is the midpoint. So the midpoint between 1 and 1.5 is going to be 1.25. I'm still going to keep the distance of 0.5 each time, so this is going to be 1.75. 2.25 and 2.75 will be my 4 midpoints. So I'm going to come back here and recalculate at 1.25, 1.75, 2.25, 2.75, and I'm going to get rid of that one. This is 7.4375, 5.9375, 3.9375, and 1.4375. So if I want to find, since there's a constant delta x here, I can say that this is 1/2, 7.4375, 5.9375, 3.9375, 1.4375. I'm going to add all those things together. So let's go ahead and do that. 0.5 times 7.4375 plus 5.9375 plus 3.9375 plus 1.4375. Close it up. And my area is approximately 9.375 square units. All right. I'm going to come back now, and I'm going to use this left endpoint and right endpoint. I'm just going to do it on here. So for left endpoint, I'm going to do 0.5 times 8 plus 6.75 plus 5 plus 2.75. Right endpoint is going to be 0.5 times 6.75 plus 5 plus 2.75 plus 0. Just want to make sure I got that right. Again, come over here. 1, 1.5, 2, 2.5, and 3. Yes. Okay. So we have 0.5 times 8 plus 6.75 plus 5 plus 2.75, and we get 11.25 square units, and 0.5 times 6.75 plus 5 plus 2.75 plus 0 is 7.25 square units. And you can see that this midpoint approximation is in between there. This one is too small. This one is too large. This one is best, though not perfect, approximation. Let me tell you what the exact answer is here. 1 to 3 of 9 minus x squared dx is going to be 9x minus x cubed over 3. From 1 to 3 is 27 minus 27 over 3 minus 9 minus 1/3. So this is going to be 18 minus 8 and 2/3. 18 minus 8 is 10. 10 minus 2/3 is 9 and 1/3. So that's 9.3 repeating. And that's a pretty good approximation of 9.3333. This one's too big or too small. This one's too big, but this is exactly right. I'm just going to skip several pages here. actually, that's it. So let me go ahead and do this as a Riemann sum with the definition here, and I'll show you how we would get this exactly. So the limit as n goes to infinity of, let's see, we had delta x was b minus a over n was 3 minus 1 over n is going to be 2 over n. I'm going to choose a representative x value that I'm going to call ci is going to be a plus I delta x. So ci is going to be, my a was 1 plus index I, and this is 2 over n. ci is equal to 1 plus 2I over n. My f of ci is equal to f of 1 plus 2I over n. So let's figure out what that is. F of x is equal to 9 minus x squared. F of 1 plus 2I over n. I is not the imaginary number here. It is just a counter, like we were using k just a little bit ago. This is 9 minus 1 squared is 1. 2I over n and another 2I over n is 4I over n plus 4I squared over n squared. This is going to be 9 minus 1 is going to be 8 minus 4I over n minus 4I squared over n squared. This is my f of ci. My area of my rectangles, my area function is going to be equal to f of ci times my delta x. So I'm going to take all this times my delta x, which was 2 over n. That's going to be 16 over n minus 8I over n squared minus 8I squared over n cubed. Now, before we go any further, I need to show you some important formulas from I equals 1 to n of a constant. C is going to be c times n. I equals 1 to n of I is going to be n times n plus 1 over 2. These are things you need to memorize. I equals 1 to n of I squared, n times n plus 1 times 2n plus 1 over 6. And I equals 1 to n of I cubed is the square of this formula. That's n squared times n plus 1 squared over 4. So now I want to write my Riemann sum, but I want to take the limit as n goes to infinity of sum of I equals 1 to n of f of ci delta x, 16 over n minus 8I over n squared minus 8I squared over n cubed, like that. And so this index here on the sum, we've already seen limits and other things where things can pass through. N's can pass through here, but i's cannot pass through the summation symbol. N's are trapped by that limit symbol. Constants can pass through both the summation symbol and the limit symbol. But I'm going to split them up into a bunch of little parts here. So this is the limit as n goes to infinity of the sum of I equals 1 to n of 16 over n minus I equals 1 to n of 8I over n squared minus I equals 1 to n 8I squared over n cubed. So right now, this is limit as n goes to infinity of 16 over n, I equals 1 to n of 1, minus 8 over n squared, I equals 1 to n of I, minus 8 over n cubed, I equals 1 to n of I squared. My formulas are over here that I'm using. So I'm just going to say if this one is 1, that's going to be n, because I'm going to make that be 1. This is 16 over n times n minus 8 over n squared times n plus 1 over 2 minus 8 over n cubed times n plus 1 times 2n plus 1 over 6. This is going to be 16 minus 4n squared minus 4n over n squared. And this is minus 8n times 2n squared plus 3n plus 1 over 6 n squared. This is 3, this is 4. Limit as n goes to infinity of 16. This is going to be minus 4. This is going to be 8 over 3. Once I find the horizontal asymptote, because this function is going to be a minus 4 times 2 is minus 8n squared minus 12n minus 4 over this is going to be a 3n squared. And I only care about the ratio of the leading coefficients because degree of the top and the bottom are the same. So let's get that to be 12 minus 8/3. It's going to be 36 over 3 minus 8 over 3 is 28 over 3, which I think I already said before was 9 1/3, or 9.3 repeating exactly. And that's how I would do it with rectangles and get an exact answer and squeeze out all my error with a Riemann sum like that. So this answer that I got up here is exactly 28 over 3 is my answer for my area. This is also the way to get it exactly. And I showed you that this process is exactly the same as this process that we call a definite integral that goes from A to B, where we use integration and we use the fundamental theorem of calculus to plug in our limits. You see that this was much easier and only took me a couple of steps here, as opposed to this took a whole lot of paper and you had to know these summation formulas here. You will get a question where you have to do it with the limit definition here. It is an objective for the class. You will not get out of the class without using the limit definition of the antiderivative at least one time. Let's see, what else did we have for objectives here? I want to make sure that I covered all the objectives. So area under curves conceptually using geometry, doing left, right, and midpoint Riemann sums, evaluate Riemann sums using the tables in my calculator, express given sums in sigma notation and evaluate in sigma notation. I did that with the and I did a definite integral and showed what happened as n goes to infinity. As I get infinitely many rectangles here, this is what I wanted to show you. So this is what I just did in the last problem. As I get infinitely many rectangles that are infinitesimally small, I'm essentially just going to be stacking all these infinitesimally small rectangles next to each other and just coloring in under the curve and squeezing out all the air. And that's what the idea of a definite integral does for me. So area is one of those things that I can use a definite integral for, but anytime that I want to add up infinitely many infinitesimally small slices of something because something is changing in every instant in time, then I'm going to use a definite integral process or this Riemann sum process to do that. All right, hopefully that was helpful to you. I can come back and do some more examples of that later as well. But that ends this discussion here. We're going to come back next time and talk more about the definite integral and the fundamental theorem of calculus. I mentioned them both this time, but we'll not do problems this way. We'll solve the same kind of area problems and some other problems using this technique that I showed you right here, this notation and this way to get the answer. That's what we're going to do in the next video, the shorter version of this that you're going to use most often, where you're going to use antiderivatives and the fundamental theorem of calculus. All right, I'll see you for the next video.